All right. Hi, everyone. Welcome back to the University of Washington Astrobiology Colloquium. I'm Mike Wong. I'm a postdoc in astronomy and astrobiology, and I'd like to begin with a quick land acknowledgement. So, we acknowledge that the UW Astrobiology program resides upon the land of the Coast Salish peoples, land that touches the shared waters of all tribes and bands within the Duwamish, Puyallup, Suquamish, Tulalip, and Muckleshoot nations. And we recognize that we, the UW Astrobiology community, benefit from the occupation and use of this land, and that it is our responsibility to mend and forge our relationship with Indigenous peoples who are an extant and vibrant members of the broader Seattle community. And I'll put some helpful links in the chat if you'd like to visit them and learn more. And now, let's admit a couple more people from the waiting room. It is my pleasure to introduce you all to Dr. Chuanfei Dong. Originally from China, Chuanfei earned his dual PhD in planetary and space science and scientific computing from the University of Michigan. He then went on to do a postdoc at the Space Science Laboratory at UC Berkeley and was a NASA Jack Eddy postdoctoral fellow in the Princeton Plasma Physics Laboratory. He is now a staff research physicist in the Princeton Plasma Physics Laboratory, and over the course of his career, he has played important roles in organizations familiar to many of us, such as NASA's Nexus for Exoplanet System Science, the TRAPPIST-1 JWST Community Initiative, ESA and JAXA's Bepi-Colombo mission to Mercury, and NASA's MAVEN mission to Mars. When he's not doing research, Chuanfei enjoys playing the guitar and singing, but that's a concert for another time. Right now, he'll regale us with star-terrestrial planet interactions in our solar system and beyond. Chuanfei, the floor is yours.
Thank you, Mike.
We're seeing the presenter view, Chuanfei.
How to make a full screen without slide show? Oh yeah.
There we go.
Okay. Yeah. Thank you, thank you, Mike, and thank you for the colloquium organizer who invited me to give a talk here today. So today I will be talking about star-terrestrial planet interactions in our solar system and beyond. Let me start with the habitable zone of our solar system. As you can see from this slide, there's a green region around the star. And both Mars and Earth are in the habitable zone, which is defined by the region around the star where the liquid water can exist on the planetary surface. And however, today's Mars has almost no atmosphere. So the natural question to ask is, where did the atmosphere and the water on Mars go, transforming Mars from an early, warmer, wet world to the cold and dry state existing today? And so far, the most efficient way to remove a planetary atmosphere is the hydrodynamic escape. And this is also the escape that exoplanetary community pays most attention, mainly because it is easy to observe, for example, from the Lyman alpha line or the helium line. But in contrast to the Jane escape, hydrodynamic escape is an organized outflow with a bulk velocity driven by the heat of the atmosphere. But however, however, today I will address this question by using the knowledge from planetary side, heliophysics, and space weather I try to address the loss of the secondary atmosphere, because the hydrodynamic escape works best for those light elements like hydrogen and helium, but for oxygen or CO2 plus those heavy ion, in general, those hydrodynamic escape does not work. And as shown on this slide, those streamlines are so-called solar wind. Basically, they are the charged particles streaming away from the star that can affect a planet. And as we all know, we can also observe solar flare from the solar surface. And but maybe some of you don't know, in general, there are a associated structure or a magnetic cloud can also release from the stellar surface. We call this as coronal mass ejection. And I also want to mention that stellar flare and the CME event have been at least partially observed in other stellar systems. So on this animation, I want to give you a big picture about a flare-CME event that occurred in our solar system on September 2017. So the box, those curves in the box is the enhancement of the stellar radiation due to the flare event. And this is also how we observe stellar flare by using, for example, Kepler and the test data. However, as you can see, there's a red magnetic cloud or magnetic bubble also ejected from the solar surface, and which can impact Mercury, Venus, Earth, and Mars during its propagation outward. And now you have a brief idea what is space weather referred to. And next, I want to give you a brief overview about different layers of an atmosphere. Most people do climate modeling know very well about the troposphere and the stratosphere. And climate people usually stop here. But above that, there's also the so-called mesosphere, thermosphere, and the exosphere. And the boundary between the thermosphere and the exosphere is so-called exobase. So in general, above exobase, the atmosphere is collisionless. So which means below exobase, a fluid model will work, but above exobase, which require a particle model because it's become collisionless. When you go even further, so the exosphere and the thermosphere is so-called the upper atmosphere. And when you go even further, it will reach the outer layer of a planetary system called the Magnetosphere. So the definition I used when I divide the different layer of the atmosphere is based on atmospheric temperature. But if we consider electron density, then we call the lower part as the neutral atmosphere, and the upper part is the ionosphere. And the ionosphere and the thermosphere are almost overlapped in the same region. So how does the sun or a star affect the planetary system? So the stellar EUV and the UV radiation can directly impact a planetary upper atmosphere. And the solar wind or stellar wind and the CME can interact with a planetary magnetosphere. If it's Earth-like magnetized, it can directly interact with the planetary upper atmosphere if it's Venus or Mars-like unmagnetized. When I say unmagnetized, it means there's no intrinsic global magnetic field. And there's certain feedback between the upper and the lower and the middle upper atmosphere. So one of the consequences of the stellar wind or solar wind planet interaction is the atmospheric ion escape from planet. So in this slide, I show you the case for the magnetized Earth-like case. As you can see, those stellar wind energy can be deposited into the polar region through the post-polar cusp. And you know, in the tail, there's also a process called magnetic reconnection, which can also convert magnetic energy into the kinetic energy, can also deposit some energy into the polar region. So when the electron in the planetary upper atmosphere become hot or energetic enough to escape away from planet, and due to the charge separation, there will be an electric field in the polar region. And this electric field can also pull the heavy ion away from the planet. And this process is the non-thermal escape process, which is not driven by the temperature itself, but also the electromagnetic force in the system. And we have developed a model to simulate such processes. And as I mentioned earlier, we can develop a MHD model. And the MHD model by itself includes the upper atmosphere and the ionosphere. And for example, the first row here is show you the case for photoionization. And the sun is on the right side. So it can ionize the upper atmosphere. And the upper atmosphere can also be ionized by electron impact ionization. And it can also be ionized by charge exchange between the solar wind proton and the upper atmospheric atom or molecule. So the first row here is show you the case happened at 4.0 billion years ago for the early Earth. The second row is during a very extreme CME event. So once those ions form in the planetary upper atmosphere, they can escape along those open field line. And this is the normal early case, and this is the extreme early case. And you can see the extreme case has more ion to escape along those open field line. And for unmagnetized case, the picture is you can understand the picture as how you dry your hair during your daily life. But one of the difference is there's an escape plume on the day side of Mars, which is also observed by MAVEN, as I will show in the next slide. The escape plume here is caused by the minus V cross B electric field. So you can imagine the solar wind is in the horizontal direction, and there's a interplanetary magnetic field, or the stellar magnetic field has an out of plane component. So when you do minus V cross B, it will give you an electric field. And the electric field that can be in the upper, can point upward, but can also point downward based on the IMF orientation. So this is what has been observed by the MAVEN spacecraft. The background here is the oxygen flux measured by the MAVEN instrument. And those particles are from simulation. So as you can see, the simulation and the observation agree reasonably well with each other. So we have developed a modeling framework to address how the atmospheric escape from Mars at both current epoch and back to early times. And we have a planetary magnetohydrodynamic model, as I mentioned earlier, which includes planetary ionosphere and magnetosphere. And we also have a whole atmospheric model for Mars, starting from the planetary surface. So include the lower, middle, and upper atmosphere. And above exobase, we need a Monte Carlo particle model to simulate that. So we also have an exospheric Monte Carlo model. And the Monte Carlo model will provide the neutral exosphere to the MHD model, and the whole atmosphere model will provide the neutral thermosphere into the MHD model. And it can, because the MHD model itself includes self-consistent photochemistry, so it can form ionosphere inside the MHD model. and those ions can escape through the stellar wind-planet interaction. At the current epoch, we have spacecraft measurement for the stellar wind condition. But when we go back to early times, we don't have spacecraft. So the way we did is the way we used is to use a stellar wind model. And the lucky thing is we can observe those stellar magnetic field from sun-like star at different age. So we can use those magnetogram or the stellar magnetic field as the inner boundary condition for the stellar wind model, such that we can simulate the stellar wind or the solar wind at a different epoch when we go back to early times. And in order to convince you, I show you a data model comparison from this model coupling framework with the MAVEN measurement. In panel B, I used the 1D spherical averaged atmosphere from the whole atmospheric model and the Monte Carlo exospheric model. In the panel C, I used the 3D atmosphere from these two models. And the solid line are from MAVEN measurement of ionospheric ion density. And the dashed line are from simulations. So overall, both panel, the data model comparison are reasonably good. But if we really want to focus some details, for example, if we focus on CO2 plus, then we can see overall the 3D atmosphere gave a little bit better agreement with our observation. So after that, we are confident to apply this modeling framework to study the Martian atmospheric escape at current epoch and back to early times. So as you know that this solar EUV radiation is the most important radiation for the upper atmosphere. So we choose 4 points during the 4.0 billion year time history, and which corresponds to 4 solar EUV condition. And when we go back to 4 billion years ago, for example, if by the way the color map scale are not identical. So if we back to 4.0 billion years ago, the upper atmosphere become much hotter on the 10 EUV radiation. I also want to mention the whole atmosphere model we used here is a non-hydrostatic model, so which include the vertical momentum equation, and not like the traditional GCM model based on hydrostatic equilibrium. And when we use those background from the whole atmospheric model, we can also simulate the exosphere at different epochs. So again, when we go back to early epoch, the exosphere also become much more extended. When I say exosphere, I mean hot oxygen exosphere. And the sun is on the right side. And one of the interesting point I want to mention is the exosphere on Mars is asymmetric around the Mars. If we see how the exosphere formed, then we will understand the reason. The exosphere is formed by the dissociative recombination of O2 plus. So when O2 plus combined with 1 electron, it will form 2 hot oxygen. And because the O2 plus ion is the main ionospheric source at Mars, so we can imagine there are more those ions on the day side than night side. So if there are more source on the day side, then there will be also more hot oxygen on the day side, so which lead to the asymmetry. And finally, we can use the thermospheric and exospheric background into the MHD model to study how the heavy ion escape from the planet at different epochs. And the model can also reproduce the day side escape plume, as you can see from here. But when we go back to early epoch, the upper atmosphere become more extended, so the asymmetry become less obvious. And here is the plot to summarize the escape of different ion species and the hot atomic oxygen at a different epoch. So if we focus on the current epoch at 0.0, we can see the neutral hot oxygen escape is the dominant escape for the heavy element, which is also true from a MAVEN observation. But when we go back to early epoch, the ion escape become more important, especially for the O+ ion, because it has relatively high or large scale height in the upper atmosphere. So it's become the dominant escaping ion back to early epoch. And the takeaway here is the total mass loss over the 4.0 billion years corresponding to a global surface, global oceans with depths about 2.6 meter. And you may ask, Mars should have more water than 2.6 meter. This is because we only consider normal solar wind condition here. And here is the comparison of the statistic between solar flare, microflare, and the super flare. So the red line here is a fit based on all the available data for the flare energy versus flare frequency. So which indicates the lower the flare energy, the higher frequency it is, and the higher energy, the higher flare energy, the lower frequency it is. So the large solar flare we observed so far is on the order of 10 to the 32 erg. And based on these statistic data, it can occur every 10 years. But I also want to mention this curve has solar cycle dependence. So if this during the solar cycle minimum, the frequency will reduced. And during the solar cycle maximum, the occurrence of the flare will increase. And we use we fit the data from the most active sun-like star here, and we can see for the most active sun-like star, the flare for the same energy of the flare, the frequency become much higher. And we can actually, this is exactly happen when we go back to early epoch for the young sun, because there's stellar observation that young sun-like star has very frequent flare. I want to use one example, what happened to Mars on 2015 March 8th. CME event just set-swept Mars, but it's lead to an enhancement of atmospheric escape rate by a factor of at least a factor of 10. But the full effect of the CME impact has not been fully observed, especially during a very extreme event. And so I took the most extreme event in the solar system with the CME energy on the order of 10 to the 32 erg. By the way, the CME energy and the flare energy are always on the same order because because there's some internal relation due to the electromagnetic theory. So as we can see, before the event, the total ion escape, the oxygen ion escape rate is on the order of 10 to the 24, which is also consistent with MAVEN observation. But during the peak of this event, the ion escape rate not just enhanced by a factor of 10, but enhanced more than a factor of 1,000. So which can potentially significantly increase the ion loss back to early epoch because the young sun has very extreme flare and CME event. So, which can also potentially give you more deep ocean back to early epoch on Mars. I want to briefly discuss the energetic particle associated with the CME event. As we, from spacecraft observation, there's always energetic particle associated with those CME events. And those energetic particle can transport through the atmosphere. And here I use Earth as example. But we can also simulate what happened to early Mars. For example, we here is the panel here is the column mass of the ancient Mars by assuming a 1 bar surface pressure dominated by the CO2 atmosphere. And the panel D here is those energy flux on the Martian surface back to early times, about 4.0 billion years ago. And the panel B here is how those the black curve are for the current Mars case. So if we focus on the dashed dotted line, we can see it can just, if we focus on the dashed line here, we can see it can just reach the Mars surface when it reaches 150 MeV, which is also consistent with the MSL observation. But when we go back to early epoch with a 1 bar surface pressure, then we need at least 6 GeV particle to reach the planetary surface. And the panel C gave you the ionization of ancient and current Mars. So one of the consequences of those energetic particle transport is they can break N2 into N and N plus. As we all know, the N2 is not that easy to be broken by the UV, for example. And so at least the energetic particle provide one of the solution to break N2 into atom and N plus. And if the atmosphere has certain methane, so through a certain form of photochemistry, the hydrogen cyanide can form through such process. We have some ongoing work by using a more self-consistent photochemistry model, but if I have time, I can show at the end of my talk. So let's go to the exoplanetary system. As we all know nowadays, our solar system is not unique. And there are a lot of similar systems has been observed and detected in our universe and the galaxy. And this is the system observed by the Kepler mission. And one of the interesting findings recently is that not all of these exoplanets has a thick atmosphere. For example, as shown on this slide, the right panel, the left panel shows you the thermal phase curve, and the right panel shows you the best fit temperature map. And the strong day-night contrast and the hot spot at the substellar point both indicate weak heat circulation and are consistent with the lack of the thick atmosphere on a planet. You can imagine, like on Venus and Mars, the temperature between day and night side are huge, so which basically give you those strong variation at different phases of the orbit. And I will focus on one of the most famous system people are interested in so far is the TRAPPIST-1 system. The reason people are very interested in this system is because there are 3 Earth-sized planets in the habitable zone of the TRAPPIST-1 system. But however, if we see the TRAPPIST-1H, the star planet distance is much smaller than our inner planet Mercury. This is mainly because the TRAPPIST-1 is an M dwarf star, so it's much smaller and dimmer than our sun, so which make the habitable zone much closer to the star. And we use the stellar wind model I mentioned earlier to simulate the stellar wind from the TRAPPIST-1 system. And the panel A show you the velocity, panel B show you the pressure, and the panel C show you the density. And the second row is the zoom in version of the first panel. And a different circle shows you different planet orbit. So the bottom panel, in bottom panel, there's a dashed line here. This is we call the critical surface, which means inside of this critical surface, the interaction between the star and the planet is submagnetosonic or subsonic in the hydrodynamic case. So I want to point out such interaction can only occur in our solar system in joint planetary magnetosphere, like how Ganymede interacts with Jupiter's magnetic field, or how Titan interacts with Saturn's magnetosphere. But in all the planets in our solar system are currently outside of this critical surface. So as you can see, if I plot the velocity, there's no clear shock form in front of TRAPPIST-1b when it's inside the critical surface. But when it's outside the critical surface, then there's a clear shock structure. And here I just plotted TRAPPIST-1b and TRAPPIST-1g. Minimum mean the minimum stellar wind pressure over planet's orbit, and the maximum mean the maximal stellar wind pressure the planet experience over its orbit. And the first row here show you the oxygen ion escape from these planets. So I plotted the ion escape rate for different planets from TRAPPIST-1, B, C, D, E, F, G, H. And we find that the time scale over which these planets can retain their atmosphere range from 10 to the 8th year for TRAPPIST-1b to 10 to the 10th year for TRAPPIST-1h, but with a 1 bar surface atmosphere. We did not consider outgassing, for example, here. And the TRAPPIST-1g, we claim the TRAPPIST-1g will probably represent the best chance for a planet in the habitable zone of this system to support a stable atmosphere over a long time period. Mainly because TRAPPIST-1H is not in the habitable zone. Otherwise, it should also be able to maintain a stable atmosphere. And I also want to mention there are 2 JWST proposals that have been selected to observe TRAPPIST-1 planet's atmosphere, if the atmosphere exists. I also want to briefly discuss the TOI 700 system, because this is the first, because TOI 700d is the first Earth-sized planet in its stellar habitable zone discovered by the TESS mission. For this study, I will focus on the different atmospheric composition. So we use the stellar wind model to simulate the stellar wind profile. And we studied basically the unmagnetized Venus-like case, unmagnetized Earth-like case, and a magnetized Earth-like case. So if we compare unmagnetized Venus-like case and unmagnetized Earth-like case, we find that the Venus-like atmosphere has the O plus ion escape rate about 2 orders of magnitude lower than Earth-like atmosphere. And when we add a magnetic field line global magnetic field line on the Earth-like case is also reduce the atmospheric escape rate by one order of magnitude compared with the unmagnetized Earth-like case. Here I want to address why Venus-like atmosphere can reduce the atmospheric escape rate by 2 orders of magnitude. So if we focus on Venus and Earth's ionosphere, we can find that the Venus ionospheric peak is at 135 kilometer altitude, and the Earth's ionospheric peak is around 300 kilometers. The reason is that the Venus, although we may think Venus is very hot, but the upper atmosphere of Venus is pretty cold. It's only about 200 K. And the Earth's upper atmosphere can reach 1,200 K. Sometimes it can even reach 2,000 K. The main reason is that the CO2 gas is a very efficient cooling gas in planetary upper atmosphere due to the 15 micro radiation. And also based on stellar observation, we know those M dwarf is even more magnetically active than a sun-like star. And so I want to briefly discuss how we observe stellar flare from those stellar systems. So the sinusoidal curve here is modulated by the sunspot or the stellar spot. However, you can see this spike structure. They are stellar flare because they are sudden enhancement of the stellar radiation, as I show you in very early animation for the flare event in 2017 September. So this is how we observe flare event from the star. And based on statistic data, we also find those M dwarf has high flare rate than K dwarf, and the K dwarf has high flare rate than G dwarf. And M dwarf exhibits super flare about 10 times more frequent than a solar type star. So we can use those flare energy to initialize the CME from star. For example, here we show what happened to a fast rotating young sun-like star. We assume the flare energy is on the order of 10 to the 32. And the rotation period of the star is about 1 day. So as you can see, the stellar CME, due to the fast rotation of the star, the stellar CME has a much broader impact region than traditional CME. So it can, imagine if a planet orbiting around such a star, it has very, very high chance to be impacted by the stellar CME due to the fast rotation of the star. And we can also simulate what happened to an Earth or Earth-like planet during such an extreme event. I want to mention the blue curve here is the stellar magnetic field or the interplanetary magnetic field. The white curve are the planetary magnetic field, but both ends connect to the planet. And the green magnetic field line are the open magnetic field line, which means only one end of the magnetic field line is connected to the planet. So we can see during extreme space weather event, the whole system is significantly compressed. And a huge amount of the oxygen ion can be escaped from the planet during such an event. And I calculate and such event can last for about 4 hours. And I calculate the escape rate can reach about 800 kilograms per second. which is pretty large. Sorry. And the big magnetic and the big bubble in the tail is caused by a process called magnetic reconnection. It can basically the magnetic field can reconnect. So those initially closed magnetic field line can be disconnected to the planet, and they can bring a huge amount of atmospheric ion away from the planet. And here is another animation. I only plotted the iso contour of the oxygen ion density. And again, as you can see, during this event, a lot of oxygen is released from the planetary surface, planetary upper atmosphere. And essentially, due to some kinetic process or dynamic process in the magnetosphere, they can escape away from the planet. And finally, I want to briefly mention the case for Mercury. As I will discuss later, Mercury has some unique feature why we want to discuss or study that. But before that, I want to mention there are two spacecraft. One just ended, and the other is on the way to Mercury. The messenger from NASA, and the Bepi-Colombo is from ESA and JAXA. The Bepi-Colombo is a twin spacecraft mission, by the way. So one will focus on geology and planetary surface, and the other, this is from ESA, called MPO, Mercury Planetary Orbit. And the other one is from JAXA, called MMO. Later, they changed it to MIO, because MIO has certain meaning in Japanese by itself. The MMO is the Mercury Magnetospheric Orbit. So it will focus on the magnetospheric dynamics, because Mercury is the only terrestrial planet in our solar system also has intrinsic magnetic field. And we have developed a model to simulate the solar wind interaction with Mercury. But the uniqueness of this model is we did not start from the planetary surface, but we started from the planetary conducting core. So as you can see, we included the mantle, crest, and the core in the simulation. But for our purpose, we mainly needed the resistivity profile of the mantle into our simulation for the electromagnetic induction response. And here's the data model comparison between our model and the messenger observation for the magnetic field data. The BY is from the magnetometer on board messenger, and the black line is from magnetometer data from messenger, and the red curves are from our magnetospheric model. And overall, they agree very well with each other. And we use very high resolution in order to capture some kinetic process. One of the unique thing of Mercury is it has a very big core. The core size can reach about 0.8 of Mercury's radius. And the core has a very important, play a very important role in the star-planet interaction, as I will show on the next slide. Because our model started from the core surface, so we can also simulate those eddy current on the conducting core surface. I want to point out the shadow sphere is the planetary, is the planet itself. So here is the planetary surface, and the color sphere is the conducting core. Is not the Mercury surface. And we are able to simulate those current on the planetary conducting core surface. And the M2 flyby mean it's a normal solar wind condition. Extreme condition mean there's very extreme solar wind condition from the sun. So during the extreme condition, we can see the current on the conducting core surface become much stronger than the normal case. And the strong current can produce external magnetic field, which actually can protect the planet from the stellar wind or the solar wind impact. And the interesting here below is a cartoon, and you can see those eddy current can produce external magnetic field. But there's a process called magnetic reconnection. So the planetary magnetic field can reconnect with the stellar magnetic field, which can remove some field line from the planetary day side. Because those close field line is the field line can protect a planet. It is because the charged particle usually cannot move across the close field line. So there's a balance between the core induced magnetic field and the reconnection process. And because Mercury has a big core, conducting core, so those external field effects become more obvious. And as I wrote here, the induction response arising from the electromagnetic coupled interior play an important role in solar wind and Mercury interaction. So imagine if an exoplanet has a very big conducting core and it's very close to the star. And the conducting core is will be able to produce those external magnetic field. And if the planet has an atmosphere, it may reduce the atmospheric escape rate by those additional magnetic fields produced by the eddy current on the core surface. So here's my conclusions. Magnetized stellar wind can enhance the atmospheric escape rate, especially during those extreme events, and therefore will affect the habitability of exoplanets in close inhabitable zones. That is defined solely based on stellar radiation. And the core induced magnetic field can or may help protect the planet, hindering the compression of the magnetopause down toward the surface. When I say magnetopause, it means the outermost closed magnetic field line. The takeaway here is the space weather and the stellar wind induced non-thermal atmospheric escape needed to be taken into account for planetary habitability. And thank you for your attention. And here's the acknowledgement for my collaborators for this line of work.
Excellent. Thank you, Chuanfei. Everybody throw up those clapping emojis. Now it's time for question and answer. You have two options for this. You can either raise your hand using the button under the reactions tab at the bottom of your Zoom screen, or you can type your question into the chat. If you wave your hand at your Zoom screen, there is only a 3 out of 38 chance that I will see that. So please use the chat or the raise hand button. And we have our first question already from Maxime Morris, who says, what is the importance of the state, liquid or solid, of the core in star-planet magnetic field interactions?
I think the core cannot be fully solid, because otherwise there will be no convection inside the core. So I expect there will be, because we don't really know what's the core status of Mercury, but because it has an external magnetic field, we believe it should be more like Earth. There's a molten core outside, then there's a solid core inside. But I think the more important thing is the core, is the temperature gradient between the core surface and the mantle, how people call core mantle temperature gradient, something like that. I think that can really decide the strength of the magnetic field. of a planet. So if I reiterate again, so which I want to say is there should be a temperature gradient at the core mantle boundary in order to generate a magnetic field based on the dynamo simulation.
Very fascinating. Maxime says thank you, and Vicky, you are next.
Hey, so as far as I understand it, there aren't any, at least spectroscopic observational constraints on TRAPPIST-1 and H potentially having a hydrogen-dominated atmosphere. But based on your escape modeling, what do you think the probability is that G and H have hydrogen-dominated atmospheres?
I think for hydrogen-dominant atmosphere, the chance is pretty low, because the reason is because the system is pretty old, about 8 billion years old, and the hydrogen and helium is very easy to escape, even by thermal and hydrodynamic gene escape and hydrodynamic escape. I don't think the hydrogen atmosphere can last for 8 billion years. Even both G and H are a little bit further from the planet.
Okay. I mean, what sort of lifetime do you think that atmosphere would have? Is it just in millions of years, or if it was hydrogen dominated?
I think for hydrogen dominated atmosphere, for a rocky planet, it should be the lifetime should be much less than billion time scale. I think it's on the order of at most 100 million time scale, or even less than that. I think for a rocky planet with low surface gravity, the chance to maintain a secondary atmosphere is much higher than hydrogen and helium atmosphere.
Okay, great, thanks, that's helpful.
All right, great question, Vicky. Still have time for a few more questions. But not seeing any. I'll just ask one of my, Abel Mendez has a question. Here we go. How many bars of CO2 are needed to keep a CO2 dominated atmosphere for a planet like Venus? Can atmospheric erosion balance from volcanic flux?
How many bars of CO2 are needed to, what does this question mean? So, Venus has about 93 bar CO2. But for the case I studied atmospheric escape here, I fixed a 1 bar CO2 atmosphere. But I want to mention, when I increased the surface pressure to 93 bar, I found that the ion escape rate only increased by a factor of, I think less than a factor of 2. So which means the surface pressure is not that really important for the atmospheric escape, because most of the atmosphere will be in the lower part of the atmosphere. And so for example, on Earth, if we assume isothermal and we assume the scale height is 10 kilometers, and we can imagine most of the atmosphere will in the first 10 kilometer altitude. So no matter how many you add, the amount you add to the upper atmosphere is not that much, and which is the dominant region for the ion to escape. I'm not sure whether I answered your first question, but for your second question, it's a very good question. I think if we observe the TRAPPIST-1 planet has atmosphere, then the outgassing will be a very important source to maintain those atmosphere. Otherwise, based on the calculation here, all the atmosphere already escape away. So I think outgassing will be a very important source to balance the atmospheric escape if it turns out a planet has an atmosphere. But of course, there's also other source like comment delivery, although I'm not sure whether there are comments in M-Dwarf system. But if we find, so basically what you propose is we need some source to maintain an atmosphere, and I fully agree with you. because here I only consider sink. There's no source in the model.
All right, thank you for the question, Abel. David, you are up next.
Okay, thanks for your talk. So I want to ask about Mars. You said that when you just have current Mars and extrapolate backwards, that you got only 2.6 meters of ocean loss. And then you said that you could consider flares, and that would enhance the loss. But then as you go back to early Mars, eventually Mars has a dipole magnetic field, which presumably would protect the atmosphere. But I don't think you said how many meters of loss you can get if you consider flares. How big does it get?
Yeah. First, I want to, you are right. The early Mars has a dipole. Actually, the surface strength can reach 50,000 nanotesla, which is a little bit stronger than Earth's surface value. But I want to mention the Martian dynamo turned off around 4.8 gigayears ago, or billion years ago. I stopped 4.0 billion years here. The main reason is because, if the first 0.5 or 0.6 billion years is very complicated, there's uncertainty about stellar parameter, and also those impact can also significantly affect the planetary atmospheric condition. So this is the reason we do not include a dipole in this study. Second, if we the ion escape rate here is on the order of 10 to the 37. But this combined with early solar wind condition and the strong EUV condition. And when I do the simulation for this study, it's also reached 10 to the 27. But it's only based on current stellar radiation. If I enhance the stellar radiation by a factor of 10, I imagine, I cannot tell directly, but I imagine the escape rate may reach 10 to the 29. And based on young sun observation, we know those stellar CME events can occur on a daily basis. And based on the current event, it's lasts about 4 hours. And also based on MAVEN observation, even after the CME event, the atmosphere needs about 1 day to recover back to the normal state. So I expect if I increase the EUV radiation by a factor of 10, I think the escape rate can at least reach on the order of 29th. And if we assume such event can occur on a daily basis, which is based on stellar observation, then I imagine the early Mars water, the depths can also increase by a factor of 50 to 100. But this, I only did one simulation here. I haven't done more self-consistent simulation for CME back to early times. So
okay,
yeah.
So you're basically saying that if you take into account the flares, you could get maybe 100 or 200 meters of water removal.
I think yes, this is my conclusion. You're right.
And also in one of your Mars slides, you put some methane in there. Or actually, you had a CH radical, and which would come from methane. I guess that's what you're saying.
Yes. But this is minor. They are not they are tracing gases. They are not the major component. Okay. This. Let me show you. I told you I have some more but that is unpublished, so I did not show it. But I can show. We have collaborated with Robin Waddles and Paul Raymer from Harvard and Cambridge. So this is what we really simulated back to early times at Mars. This is simulation result. But this is not based on my simulation. This is based on the model developed by Paul Raymer at University of Cambridge. But the initial purpose of this slide is I want to say is, he simulates the hydrogen cyanide production produced by UV. And he also used the same code to simulate the hydrogen cyanide produced by those energetic particles. And we found the production, this can be much higher than UV only source. So we think those energetic particles back to early times can be very important for prebiotic chemistry.
Okay, that's interesting. But yeah. I guess the question is, where does the methane come from? Because you need a lot of methane to drive the production of HCN.
Right. I can tell you, we don't know.
Yeah. Well, you can get it from impacts big impacts where the iron core reacts with water and makes hydrogen, and then photochemistry makes methane. But otherwise, it's difficult.
Yeah, sure. I can also show you one slide about we have done Mars atmospheric escape from magnetized Mars with different magnetic field strengths. And you can see the escape rate dependence on the dipole strength is non-monotonic. So which means without a dipole and with a dipole, they are not the minimal or maximal value. With certain strength of the dipole, it will give you the lowest ion escape rate. This is also unpublished, but the relation are non-monotonic. This is very interesting. It's not.
Is there a simple explanation, like, for example?
Yes, I can give you a simple explanation. Yeah, because for unmagnetized Mars, as I also from MAVEN observation, we know there are two escape channels. One is from the tail, and one is from the base plume. Right? I talked about that for the electric field. So there are two channels. So, but with dipole increase and keep increase, the day side channel disappears, and only those escape from the polar region is possible. So there's a balance, and on the other side, when the dipole become more and more stronger, it will absorb the cross section to interact with the stellar wind also become stronger. So if I use a simple line, a simple sentence is the day side escape rate, the day side escape component decrease with the dipole strength. The polar region, the escape from the open field from the polar region increase with dipole strength because the cross section of the interaction become larger. So you can imagine if one line is decreased, the other line is increased. So when you add them together, it will give you a non-monotonic trend. Because basically there are different loss channels.
Okay, thank you.
All right. I'm going to move us along to our last question from Yuk-Chun Chan, who snuck it in before we reached 4 o'clock. So I feel bad if we don't get to it. So Yuk-Chun puts in the chat, do you think the escape of atmospheric ions from the ancient Martian atmosphere would leave any detectable records on Phobos's surface? Came across this idea when I was reading a recent paper. I am curious whether your model can simulate this kind of planet-moon-sun interactions.
Yes, we can. I probably know the paper Yak discussed. It's published in Nature Geoscience. you know, the similar idea also apply to our Earth. For Forbes, I feel maybe it's a little bit difficult. But as probably you already know, there's a MMX mission from Japanese JAXA called Mars Moon Explorer. So it will take sample from Forbes. But you know, I feel Forbes is too small, so it's not clear to me what's the if there's surface tectonic motion or those kind of things. But if we back to our moon, we can also apply those ideas to study the lunar regoliths or lunar rocks to potentially find those evidence from early Earth's atmosphere. But I think overall, I agree with your idea. It's actually someone bring to me this idea back to 2016 when we discussed about MMX mission. So we try to see whether it's possible to do the sample analysis from the Forbes to potentially constrain the early Martian atmosphere. I feel it's possible, but it's maybe difficult because first, it's too small. The moon is too small. Second, I remember someone told me maybe it's not easy for the Forbes to return those historical data back to early times or maybe because of the surface space weathering effect or some I cannot remember the overall I think people told me for Forbes the sample can only tell you the atmosphere from Mars in recent several at maximum million years, cannot go beyond the billion time scale.
Okay. Yeah, very fascinating. Great question, Yuk-Chun. And let's thank our guest, Chuanfei Dong, one more time. And we'll see you back here next week for a Tanya Bosak's talk. Take care, everyone.